So basic continuous time signals. So these are some basic time signals, continuous time signals which are used in signal processing quite often. The first one is the unit step function. The second one is the unit impulse function. Third one is the complex exponential function and sinusoidal signals. Unit step function we have in our last class already discussed. So if you have any signal like this, time and amplitude, and this step function usually it is having an amplitude of 1 and it starts from t equals to 0 and it is continuing till infinity. Then this kind of signals are regarded as unit step function. So we can also have a delayed unit function, a unit step function also. Okay. In the next case we have unit impulse function. In the unit impulse function we have already discussed about delta t, right? So what is delta t? Delta t is nothing but an impulse signal at t equals to 0. Okay. Now if we have some function like this, delta t minus k, so what happens? This function, if you see delta is there, that means it is an impulse function, but we are also having a summation of some numbers, right? So what are these? This is an equation for impulse strain function. Impulse strain function. So these are the impulse functions which are present at numerical integers. Okay. So where this is useful? This is useful during the sampling of the continuous time signals. Okay. So we have already discussed about this impulse strain and impulse function and unit step functions in our previous classes. So I'll be moving forward now. So this is the equation for the unit step function, and if there is any delayed unit step function, then it would be something like this. So this is the equation for the delayed unit step function. Now similarly, unit impulse function. So we all know at delta t not equals to 0, we are having 0, and t equals to 0, we are having an infinite a. However, the area of the direct function or the unit impulse function, it is 1, and hence we consider that the amplitude of the unit impulse function is 1. However, in practicality it is considered as 1. However, theoretically it should have an infinite infinite amplitude. Okay. So this is how an impulse function look, and this is the delayed impulse function. And the sampling property, as I was telling you, it is being when you multiply this impulse function with a continuous time signal, so at whatever location this impulse function is present, the output would be that particular value at that instance. Say for example, we are having a temperature versus time curve. So suppose at time small a we have a direct impulse. So what should be the output? We will be getting a single point at A, okay, over there. So when we talk about impulse strain, then at discrete times you will be having these amplitudes like this. Okay, so this property is called the sampling, that with any given continuous time signal, when you multiply the direct impulse function or the impulse train, then at those specific locations where we are having the direct impulses, at those locations we will be getting the values of the whatever the variable is. Okay. Now the shifting property. So again, let us take that temperature versus time graph. So at initial location, at initial point, we have, say, impulse function at t equals to 0. So the resultant output we will be getting the x of 0. That means temperature at 0 time. Okay. Now suppose if I shift it to any other place, say at time equals to a, then when I have shifted the signal to this impulse function to time equal to a, we will be getting the value of x of a at that location, and this is what it has been denoted with this equation: integral of minus infinity to infinity ft, which is nothing but the xt, right, multiplied by delta t minus alpha dt, which gives us the alpha value. So by whatever fraction you are delaying the impulse function, at that location you will be getting the amplitude of the complex signal, of the continuous time signal, and at all other locations the values would be 0. Now coming to the complex exponential functions. So if you see the complex exponential function, it is given by xt equals to e to the power j omega naught t, and it can further be broken down into cos omega t plus j sin omega naught t. Okay, so you can have exponentially growing or exponentially decaying exponentially decaying signals, and this kind of signals, they are regarded as the complex exponential signals. Now you have the general complex exponential signals, which is given by xt equals to e to the power st, which can be again written as e to the power sigma plus j omega t. Okay, now this can again be rewritten as e to the power sigma t cos omega t plus j sin omega t. Now this form of the exponential function, it is regarded as the general exponential signal. Okay, whose real component is e to the power t sigma cos of omega t, and the imaginary part is e to the power sigma t sin omega t. Okay, now herein the exponentially the signals are exponentially increasing when your sigma is greater than 0, and it is exponentially decreasing when sigma is less than 0. Okay, so you can see it in the previous slide. Now coming to the real exponential signals. So in the real exponential signals, what happens is that when this j omega component, it is being suppressed, that means it is having a this component is 0. Okay, so when this component is 0, this equation becomes xt equals to e to the power sigma t, where basically s is equal to sigma, which is a real number, and it reduces the general exponential general complex exponential signals into a real exponential signal. Again, over here, depending upon the values of the sigma, it can be exponentially growing or exponentially decreasing signal. Now coming to the sinusoidal signals. So sinusoidal signals, it is a kind of sinusoidal signal. Xt equals to a of cos of omega naught t plus theta, where a is the amplitude, omega naught is the radian frequency in the radian frequencies, radian frequencies in radians per second, and theta is the phase angle in radian. Okay, and the fundamental period, it is given by T naught equals to 2 pi by omega naught. Okay, in our last class we have done some numericals. Basically in the discrete time domain it is basically the same. Okay, so from here 1 by T naught, it is equal to f0 in hertz, and this f0 it is regarded as the fundamental frequency. Okay, and this fundamental frequency, it is given by omega naught equals to 2 pi f naught. Okay, so this is an example of a continuous time sinusoidal signal. Now coming to the basic discrete time signals, the same thing, but in the discrete time domain we have the unit step function, unit impulse function, complex exponential sequences, sinusoidal sequences. So see, the same thing, from n equals to 0 to infinity you will be having an amplitude of 1, and it will go on. And then we can also have the signal in a delayed form, u of n minus k. Then unit impulse function, again if you see delta n equals to 1 for at n equals to 0 and 0 for n not equals to 0, and again you can shift it to any other position by varying the values of k. Now just like the continuous time complex exponential signals, we have discrete time complex exponential sequences. You see over there, here and here. The rest of the things, they remain the same. And over here if you see, omega naught by 2 pi equals to m by capital N, where m is a positive integer and n becomes periodic when it is a rational number, right? We have discussed in our previous class. Why you people are giving a blank face? Anyway, so again general complex equation over here. So if you see c equals to 1, a equals to alpha equals to e to the power j omega naught, if you have it, then we can get a general complex exponential thing. And for the real exponential thing, this alpha should be, both c and alpha, it should be, these should be reals. Okay. Now the sinusoidal sequences, again the same thing, xn equals to a of cos of omega naught n plus theta, where omega naught, it is the frequency and theta is the phase. Now coming to the systems. So what is a system? Okay, what is a system? A system is defined as a mathematical model of a physical process that relates the input signal to the output signals. Okay, say for example we are having an inverting amplifier whose transfer function is t. We give a signal xt as the input and we get a signal yt as the output. Okay, so what happens in an inverting amplifier? Yt equals to minus v0 by v in into xt, right? Now what is this? This we call it as gain, which can also be written as t transfer function. Okay, so we can write it down, yt equals to t into x of t. Now see, this is what it has been written, y equals to t into x into t. Okay, y equals to capital T into x. Okay, so this capital T, it is the transfer function, and this varies from system to system. So I have given the example of inverting amplifier. In the non-inverting amplifier, it would be sorry, no, it should be R2 by R1. No? आप लोग भी नहीं बता. R2 by R1, right? So in non-inverting amplifier, what it should be? 1 plus R2 by R1, right? So our transfer function, it becomes capital T. I hope all of you know about this gain of the inverting amplifier and non-inverting amplifier. Basic analog electronics class you must have done in your BTech level, right? You didn't do? Okay, then you have to go through the stuff. So it comes under biomedical instrumentation. Maybe the teacher will be teaching you. So the main thing is that what we want to say is that what is a system? A system is nothing but a mathematical model. In the case of non-inverting amplifier, 1 plus R2 by R1. So this mathematical model is for the non-inverting amplifier. For inverting amplifier, it is minus of R2 by R1. Okay, if you take this integrator, you will be having some mathematical model. So if you give some input, you will be having some output. And the most important thing is that your output is nothing but the multiplication of the transfer function with that of the input signal. Okay, so your input signal is getting multiplied so as to get an output. Okay, now these inverting amplifier or non-inverting amplifiers, we give a single input and we get a single output. So this kind of systems, they are regarded as single input single output system. Single input single output system. Similarly, if you think of the differential amplifier, where you give two different signals and you get a single output, they are regarded as multiple input single output systems. Okay, alternately, if you talk about the multi-parameter systems in a medical hospital, multi-parameter systems, what they are nothing but, if you see, if a patient is in the ICU, so what they will do, they will put all the sensors on the body. Say for example, SpO2 sensor would be there would be a PP sensor, there would be a heart rate monitoring sensor, there would be ECG electrodes, there would be respiratory probes attached near to the nose of the patient. So you are giving multiple input to the multi-parameter system, and you are getting an output which is having multiple, which are multiple in number. Okay, so if you are having this respiratory sensor, you will get the respiratory output. If you are having the ECG sensor, you will be getting the ECG output. Okay, so when you are having all this, so what is happening? Such kind of system, they are regarded as multiple input multiple output systems. Okay, now classification of the systems: continuous time and discrete time systems, systems with memory and without memory, causal and non-causal systems, linear systems and non-linear systems, time invariant and time varying systems, linear time invariant systems, LTI systems. Now these LTI systems, they are basically a combination of both linear systems and time invariant systems, and all biomedical signals usually which are used, not the what you call the AI powered or feedback systems, error minimizing systems, except those. Usually whatever the kind of amplifier we can think of, say for example the ECG processing system or EEG processing system, they are usually linear time invariant systems. Why linear time invariant systems? Because they are both linear system and they are also the time invariant system. Okay, then we have stable and unstable systems, and lastly the feedback systems. Now continuous time and discrete time system, what is the difference? The continuous time system, they would take input as the continuous time signals and output that will be generated, they are also continuous time signals. Whereas in the discrete time systems, input is discrete, output is also discrete. Okay, systems with memory and without memory. Okay, so if you consider any systems with resistance, they are taking the input and they are just passing the signal to the output without any delay. So what I mean to say is that for the computation of the present present output, no previous inputs are taken into account. No previous inputs are taken into account. Whereas when we talk of the systems that are being developed using capacitors and inductors, what happens is that the present output, it is being affected by the past inputs also. Okay, so those kind of systems, they are regarded as memory systems. They are regarded as memory systems. Then comes the causal and non-causal systems. So say for example, this is the time and this is the amplitude here. So the current input, the current output, say at t equals to 0, it would be causal only and only when your all the signal components are towards the left hand side of the output signal. Okay, so what does that mean? That means the current output, it is only and only dependent on the past and the present inputs. Okay, they are the current output, it is only and only dependent on the past and the present inputs. Okay, say for example, if the signal, it starts at t equals to 1, what will happen? T equals to 0 is the present instance in our case. T equals to 1, it appears in the future. So if something appears in the future and if you are taking that into account for calculating the present input, then it is a non-causal system. Okay, so over here if you see, there are two equations which have been given. So say when y equals to y is 0, the t is 0, so for y0 we get x of 1. Okay, so y of minus 1, इसका मतलब है x of 0, and y of 1, इसका मतलब this means we have x of 2. In all the things, if you see, for 0, for y equals to 0, that means the present instance, we need to have a signal from the future. Similarly, at y equals to minus 1, again the signal needs to be from the future. Y equals to 1, again the signal has to be from the future. Okay, that means this system, it is non-causal. Okay, then let's consider the second one. Y equals to 0, now y of 0 equals to x of minus 1, right? Oh, sorry, x of 0, y of 1, x of minus 1, then y of minus 1, x of 1. Now in the first two cases, y equals to 0 is dependent on the input at the same time. So this should be a causal system. As per this, y1 mein we are taking the input from the x of -1. So again from here it should be a causal one. But in the last one, if you see y of -1, for the case of y of -1, it is taking input for x of 1. So this is non-causal. Okay, so which one should we take? So we have to consider the system as a whole. If a system is non-causal even at a particular period of time, that means the system is non-causal. Even if it is single point, it is non-causal, that means it is a non-causal system. So the second system, it is non-causal in nature. Okay. So again we are having these things. We have just discussed y of t equals to x of t plus 1. So it is a non-causal system. This one also we have just discussed. Okay. Yeah. So now coming to the linear and non-linear systems. So what is happening over here is that, say for example, we take the example of the non-inverting amplifier. So the gain over there, it is given by say 2. Okay. So in the first instance, what we do, we give a value of x as 1. So what should be the output we will be getting? We should be getting 2, say y1. x2 is 2, so y2, it would be 4. So y1 plus y2 equals to 6. Okay. Now, say for example, I add up x1 plus x2, so it comes out to be 3. Okay. Now, what should be the y dash? So x dash equals to x1 plus x2. So what should be the y dash? So this is 3 multiplied by 2. That is again 6. Okay. Since your y1 plus y2 for the independent x1 and x2 is 6, and when you are combining both x1 and x2 and giving it as the input to the system, that is also 6, and since both say A and B both are same, these kind of systems, they are regarded as linear systems, and that is what it has been provided over here in this equation. This is the meaning of this equation. Okay. Now coming to the homogeneity or the scaling. So same thing, scaling में क्या है? Just a scalar quantity. Just a scalar quantity. So suppose I multiply this factor with say multiplied by 2. So my x2 dash, it becomes 4. So y2 dash, it would be 4 to the 8. Okay. Now if I take this 4, I multiply it with the again it is 8. So that is the scaling. So when you are multiplying the input with a scalar quantity, the whatever will be the output, and if you take the original input and get the output and again multiply the output with the system with the scalar quantity whatever we have taken, if both these things they are equal, then we can say that it is a homogeneous system. Okay. So by adding these two, additivity and the homogeneity or the scaling function, scaling property. If we combine these two, we get a condition which is regarded as superposition property. And this superposition property, what it says is that if I use a1 x1 as the input and if I use a2 x2 as the input, then my output, it should be a1 y1 plus a2 y2. Are you getting my point? यहाँ से आपको पता चल गया होगा. If you have understood the additivity and the homogeneity, then it should not be a problem for the superposition property. Any doubt? कुछ blank faces दिख रहे हैं? Okay? No? Okay, very good. Now let's take some examples. So over here we have yt equals to t multiplied by xt. So suppose we have, when we have x1, so we get y1 which is equal to t into x1. x2, for x2 we get y2 t multiplied by x2. Okay, so y dash, it is equal to given by t into x1 plus x2. Okay, t equals to x1 plus x2. That means we are adding up these two numbers here. Okay, and y double dash is when we are adding up both the numbers, both the inputs, x1 plus x2. Okay, so if you see C and D, they are equal. Since C and D are equal, it is a linear system. I gave you the example over here. First of all, what we did, we added the outputs. Okay, we added the outputs, and the second stage, what we did, we added the input and calculated the output. Right? Here also we have done the same thing. We got the equation. For x1, what should be the y1? We calculated that. For x2, what should be the y2? We calculated that. Then y dash is nothing but the addition of the y1 and y2. Right? And in the third case, y double dash, it is the addition of the inputs, and just in the place of the x we have put this addition. Now both of these should be equal. We have seen in the example here C and D are equal, right? So this is a linear system. Now coming to the next one, yt equals to x squared t. So x1 equal to x1, when you give x1 you get y1 equals to x1 square. You can also write it like this. For x2 you get y2 x squared 2 x2 square t, and then y dash, what you get, x1 square plus here multiplied by this thing. Okay, now look into this thing yt, what it should be. So what this is basically, x of t whole square. Now we have to change this input. So x1t plus x2t whole square. Are you getting my point? We are changing the input signal. We are changing the input signal. Previously we have added the output signals, this thing. So it is y1 was x1 square t, y2 was x square x2t x2 square t, right? So it was this one. But in the fourth stage we have to calculate when the input is changed, and when the input is changed, input is this one, x1t plus x2t whole square. Now here C and D, they are not equal, hence it is a non-linear system. Similarly, if you get into yt equals to xt square, this is very interesting to see. For x1 we get x1 t square, for y2 it is x2 t square. Okay, so y dash is x1 t square plus x2 t square. Y double dash also, it is x1 t square and x2 t square. Okay, why? Because x is a function of t square, you cannot change that. In the previous case, x is a function of t, and this is basically x, it was the square. Herein the square is within the t, so x is basically the function of the t square, so you cannot change that. So here your input is basically x1 t square plus of x2 t square, and that's why you have got this one. So this is a linear system, and this one we have already discussed in the previous slide, so I am not again continuing with that. Now coming to the time invariant and time varying system. Why do you need a time invariant and time varying system? This is because when we talk about the biomedical signals, so what happens, the systems should be time invariant. Why this time invariance is needed? Say for example, what happens in time invariant system, you have a system, if you give a signal now, you will be getting an output. Now if you delay the signal or advance the signal and then give the input to the to the system, what happens, regardless of the delay or the if you forget that, the nature of the output should be same. Otherwise what will happen, if you are analyzing something now and if you are analyzing after a certain period of time, both the analysis will be different. Okay, so whatever the output you are getting, that should not be dependent on time, and this is what is called time invariance. If the processing varies as you delay or advance the signal, or in other terms, if you shift the signal, then it is regarded as time varying system. However, we do not want a time varying system, we want only the time invariant system, because if by shifting any kind of signal, whether delaying or advancing, if the nature of the output changes, that means our analysis will be becoming incorrect. Okay, so this we need to understand. So let us take some example that will give you some understanding how to calculate this thing. So yt equals to t into xt. So first the signal is delayed, which is, and the output is given by y of t comma k, y of t comma k, which is equals to t multiplied by x of t minus k. That means the signal has been delayed. Okay, so yt comma k, it is the signal due to the delaying of the input, due to the delaying of the input. Okay, on the other hand, in the second case, we have to find out the output when the time is being tailored with t minus k. So when we go for the t minus k, so this t, this will also change, okay, to t minus k and x of t minus k. So in the second case, t will be replaced with t minus k. In the first case, we were delaying the signal. In the first case, we were delaying the signal. In the second case, we are not delaying the signal. we are just replacing t with t minus k. Wherever we will find t, we will be replacing it with t minus k. If it is n, we will be replacing it with n minus k. Okay. So after we do both of these, delayed output and by replacing time, delaying time, if we both 1 and 2, if they are varying, then the system is regarded as time varying system. In the second case, in the second example over here, yt equals to x square t. So delaying of the signal, see, same. When we are replacing t with t minus k, it is also the same. So this system, it is time invariant system. In the third case, yt equals to xt plus 5 of u of t. Okay. In the first case, we are delaying the input. So input is here. So input has been delayed, see. But this u of t, it is not a signal. It is not a, it is a signal. It is not an input signal. Okay. So since it is not an input signal, it will remain as it is. Whereas in the second case, where t will be replaced by t minus k, if you see, in all the cases it has been changed, and due to this reason 1 and 2 both are differing, and hence this system is a time invariant system, time varying system. Okay, sorry. So it is a time varying system. Now coming to the last example of here, this section, time varying section, yt equals to x of t square. So yt equals to x of t square minus k, and here you are having t is being replaced with t minus k, so it becomes t minus k whole square, which again become time varying system. Okay, time varying system. So in the previous case, if you see in the over here, it was a linear system. Here it is time varying system. So combining these two, we can say this system is not an LTI system. Similarly, over here it is time invariant. Okay, but if you see over here, it is a non-linear system. So again, it is not an LTI system. So these two systems cannot be used for conventional biomedical signal processing techniques. Okay. So this is what linear time invariant systems. So they have to follow both the linearity and the time invariance principles. Now the stable systems. What are stable systems? So usually in biomedical systems or any other systems, there is a word called BIBO stability, bounded input, bounded output, stable. Say for example, again I will take the example of non-inverting amplifier. So you have an amplifier which you have designed. You give an input Xi, you get Yi. Okay. So if you give a finite input, you will be getting a finite output. If that is the case, that means the system what you are developed, it is a stable system. Okay. But however you say, over here the system is being operated at plus minus 12 volt, so the operation range is plus minus 10 volt. Okay. Now if you give 24 volt as the input, it is way above the operational range. So what the output you will be getting? You will be getting a saturated output. So that signal, 24 volt signal, it is not a bounded input signal. That means the system has not been designed to work in that particular range. Okay. So since the input itself is not bounded, your output is also not bounded. So your system is not stable for that particular system. So when we talk about the stability, that stability has to be within a particular boundary condition which you need to set. So that's why the stability is defined as the bounded input, bounded output, stable systems. That means if you give some finite input within the boundary conditions, you will get a finite output within the boundary conditions based on which you have designed the system. Okay, so this is what it has been written. Modulus of x should be less than equal to k1, which should be your boundary condition, and the corresponding the output is also bounded and defined by y less than equal to k2, which is again the higher limit of the boundary. Okay, and both this k1 and k2, they are the finite real constants. Now feedback systems. So it takes feedback from the present instance and it helps in the generation of the output. Say for example the integrator, or even the inverting amplifier, non-inverting amplifier, whatever you discuss. Okay, so if you see, so this is a non-inverting amplifier and it's given by right. So if you see, the output is taken into consideration to calculate the output itself. Okay, so this is the feedback loop. So from the output you are taking some information and you are putting it back into the system to compute the output itself. Those systems, they are regarded as the feedback systems. Okay. So with this we complete this chapter. Next topic, where we will discuss about the different transforms. So the first one is Fourier series, Fourier transform. Then we have discrete time Fourier series, discrete time Fourier transform, discrete Fourier transform, Laplace transform, and Z transform. So Fourier series, as we all know, what do you mean by Fourier series and why it is important? Fourier series is important because we can analyze any periodic signals. Okay. So we have already discussed that there are two basic periodic signals. The first one is the sinusoidal signal and the second is the complex exponential signals. Okay. Now this is the equation for the Fourier series. So if you see, we have xt, which is given by summation of k equals to minus infinity to infinity ak e to the power j k omega naught t. Okay. So here, if you see, here we have complex exponential signals, which are again periodic signals. So from here, what do we get? We get that any signal, any periodic signal xt can be represented by the summation of various sinusoidal waves or different frequencies whose amplitude can also be varied by varying this value ak. Okay. So another form of this Fourier series equation is xt equals to a naught plus summation of k equals to 1 to infinity 2 of b dash k cos of k omega naught t minus c double dash k sin of k omega naught t. Okay. Again over here, if you see the signal xt, which is periodic in nature, which we consider as a periodic signal, they can be constituted of various sinusoidal waves. Okay. So here one example of square wave has been given. So the first one is the square wave, and then uh, we can see one sinusoidal wave has been added, then a series of sinusoidal waves have been added, and slowly when we are increasing the different sinusoidal waves or different frequencies and different amplitudes, and we add those up, the reconstructed signal, it is similar to that of the this pulse wave signal. Okay. However, if you see at the what you call constant amplitudes, whether it is zero amplitude or the high amplitude value of the square wave or the pulsed wave, we are having some corrugations. These corrugations are regarded as ripples. Okay. And then apart from that, at the discontinuities, we have some increased amplitude values, and these discontinuities, these are regarded as Gibbs phenomenon. Okay, these discontinuities, they are regarded as Gibbs phenomenon. Now why this is happening? This is happening because the answer lies in the equation itself. If we look over here in the Fourier series equation, what is happening is that we are saying that infinite number of sinusoidal waves, they are being used for the reconstruction of any periodic signal. However, in practicality, use of infinite number of signals is not possible, and due to this reason, what happens is that the reconstructed signals, they are nearly similar to, or you can say not nearly, you can say similar to the pulse wave, but it is not the same. Okay. And this is because the reconstruction of the signal, it is being carried out using finite number of sinusoidal signals. Okay. Similarly, if you have a sawtooth wave, again we can generate the sawtooth wave by adding up various by adding up sinusoidal signals of various frequencies and amplitudes. Now coming to the Fourier transform, so all of you know that Fourier transform, it is being derived from the Fourier series itself. However, if you look into the Fourier series, we discussed that the Fourier series is capable of analyzing periodic signal. Okay. On the other hand, Fourier transform, it is used for anyone? It is used for the analysis of what kind of signals? Aperiodic signals. Is it correct? It is correct. Anything else? Anyone? Yeah, it is capable of handling both aperiodic and periodic signals. Why? Can you explain? Why periodic and aperiodic? If we consider the Fourier transform, the first assumption what we get is that a non-periodic signal may be assumed as a limiting case of a periodic signal where the period of the signal approaches infinity. Okay, what is the period? So in our last class, one of the last classes, we have discussed that a periodic signal, it is being given by xt equals to x of t plus capital T, where capital T is the time period. Okay. So whether you add or deduct the time period for a periodic signal, the signal would be the same after you add up the t or deduct the t, right? Now here what is called, it is regarded as that any aperiodic signal, they are being regarded as periodic signal. And how they are regarding as the periodic signal, they are saying that the signal is periodic at capital T tending to infinity. Okay, at capital T tending to infinity. When the value of capital T is infinite, then we regard this the even the aperiodic signal as the periodic signal. Okay, so with this assumption we start. Okay, so say for example, if you take a periodic signal, since it is ever continuing, okay, right? So what happens at capital T tending to infinity also it will be periodic. Okay, I don't know whether you got my point or not. Suppose we have a sinusoidal signal like this. So if you consider this T period, then what happens? It is periodic. If we move this T to the next T, it will be periodic. Now from here to here if you take, it would be 2T. If you take that period, it will be again shift the signal towards the right or towards the left, it will be periodic. Similarly, if you go for 3T, it would be periodic. Similarly, if you go for T tending to infinity, it will be periodic. So when we talk about periodic signals, so what is happening, even if we consider that capital T is tending to infinite, then also the signal would be periodic. However, in the case of aperiodic signal, what will happen? We are at small time durations, the signal would be non-periodic or aperiodic. However, we are considering that, or we are assuming that capital T is at capital T tending to infinity, the signal becomes periodic in nature. Okay, so with this assumption we start the derivations. I am not going into the derivations, you can look into the derivations later on. So with this assumption, as we start the derivation, we get to the Fourier transform. Okay, and then again for any specific transform you would have a an inverse transform, and in this case it is the inverse Fourier transform. So when we apply the Fourier transform on the signal xt, we get to the frequency domain, and when we apply the inverse Fourier transform on which component we will be applying, we will be applying on the capital X j omega. When we apply the inverse Fourier transform, we get back to the time domain signal. Okay. So this figure, it is self-explanatory. So what happens is that we are having the signal. If we apply the Fourier transform, we get to the frequency domain. क्या हुआ आपको? You want to go? Okay. If you want to go, you may leave if you are not feeling well. And if you want someone to accompany you, you can take someone who will be. Okay. So yeah, once you go to the frequency domain, then again if you apply the inverse Fourier transform, you get to the time domain. Now why this? Why we are interested in first going from time domain to the frequency domain, and then again from frequency domain to time domain? Why this is so? This is because I hope you have started doing this biomedical instrumentation laboratory. You must have seen that when you are taking some signal, what happens? You are getting time versus amplitude plot. But what are the frequency components hidden in this plot? We don't know. So if you apply the Fourier transform, so what we get is that we get a frequency versus amplitude plot, and at whatever frequencies the signal components are there, monotonous frequency components are there, you will be getting some amplitude values over there. Say for example, at 50 hertz, at 100 hertz, I'm just giving you an example, okay? 150, say 200, okay? Now say for example, you got this signal and you can see that you are having a 50 hertz. So you might be having some corrugation over here. So you don't know whether these corrugations, which are basically the noises, uh, it is a 50 hertz noise or not. You don't know. So how do you ascertain that what type of noise is there? Okay. So in that case, when you do the Fourier transform, you will see that apart from the signal components which are present in the signal, you also have a component or an amplitude at 50 hertz. Okay. So from there, you can say confidently that this signal, it is corrupted with 50 hertz power line interference. Okay. Now, once you do that, what happens is that you can apply band pass filters over there. You can design the filters as per your wish, and you can use those filters, and you can eliminate the noises as per your requirement. Okay, you may eliminate the band pass filter. You can use band stop filter. Okay, you can use band reject filter depending upon the frequency components that are present. Okay. Now, what happens? Suppose you have applied the signal component, you have analyzed the signal. Okay. Now you have seen, okay, after band pass filtering, this 50 hertz noise is not there. But in real life, we cannot work on this frequency domain, because in real life, what is our continuous variable? Independent variable. Independent variable is time. So we are habituated to analyze the signal in the time domain. So to look at the image or the signal component which we can perceive and analyze in a better way, we again need to go back to the time domain signal. Okay. So this is the need of Fourier transform, and this Fourier transform, it has been used in most of the scientific fields. You talk about geology, you talk about seismology, you talk about medical imaging, you talk about space industry. Wherever you want to discuss, wherever there are any digital processing is happening, you will find that Fourier transform, it is helping us in some way or the other. Okay, so it is till date one of the most robust transform, and it has not been replaced with any other transform for analysis. Okay, so you can see it has been there for since ages. So you can understand or appreciate the importance of Fourier transform, okay, in signal processing. Now the thing is that, so these are the periodic and aperiodic signals it has been shown. Yeah. Coming to this system, we have discussed about the LTI systems. When we talk about the LTI systems, if we give an impulse input, if we give an impulse input to the system, we get impulse response of the system. This is impulse input. When we give impulse input, we get impulse response. Impulse input means we have already discussed about delta t. That means at t tending to at t0, we will be getting an impulse. Okay, that's it. So when you do that, at 0 instance, you get the input, and you get the output. So this output, it is called impulse response, and any system, whether continuous time system or discrete time systems, they are regarded as its characteristics are being described by this impulse response. It is specific for a given system. Okay. Now, when we have an input xt, if we give the input xt to an LTI system having an impulse response of h of t, then we get, or we can predict the output yt, which is given by xt convolution of ht, xt convolution of ht. Okay. Now convolution, it is slightly mathematically tedious form. So what it is being done is that if we take the xt input and if we perform Fourier transform, we get to x of omega. Similarly, if we have ht, if we perform Fourier transform, we get h of omega. Okay, we get the input, and herein we get the output y of omega. It is equal to x of omega multiplied by h of omega. Okay, so we have got the output in the frequency domain, and then when we apply inverse Fourier transform, we get the yt over here. Now, performing multiplication is much easier as compared to the compared to performing the convolution. Okay, so many a times you will find that this approach is being followed. I mean to say that the output is being computed in the frequency domain, and then through inverse Fourier transform we get to the time domain signal. Now coming to the Fourier analysis of the discrete time signals. So just like the continuous time signals, for the discrete time signals we have discrete time Fourier series. So the first one is the synthesis equation and the second one is the analysis equation. Again over here, if you see the similar equation you will be having, see these complex exponentials are there, which are periodic signals. So any given signal, they are basically computed of a series of sinusoidal signals of different frequencies. Okay, because if you see k omega naught, it is varying. K omega naught, it is varying. Now coming to the discrete time Fourier transform. So similar to the discrete time Fourier series, normal Fourier series to Fourier transform, we have some transition. Similarly, in the discrete time Fourier series to discrete time Fourier transform also, this same hypothesis is being applied, that discrete time aperiodic signals, they have a what you call time period which is tending to infinity. Okay, over here also if you see we have discrete time Fourier transform and inverse discrete time Fourier transform equation. Now in the discrete time Fourier transform equation, what you are having, again see addition of some complex exponentials of different frequencies, right? Now if you look into the IDTFT, what is happening, we are having an integration. Okay, we are having an integration. So integration, it is a continuous process, it is applicable for the continuous process. So even though we are, for the forward transform we are using the discrete equation, but in the inverse transform we have to use a continuous function. We have to use a continuous function, right? Now the digital systems, they are not able to handle the continuous functions, they can only handle finite systems. Okay, due to this reason there was a need for another transform, which we call as discrete Fourier transform. Okay, we will come to that. Just before that, the same analogy what I discussed about you some time ago, that if you are having an LTI system, then its input output relationships, how we can do it in the discrete time domain. Using the same analogy, this you will be able to appreciate the input output relationship of the LTI discrete time system. Okay, the same analogy it happens over here. So we have the xn, we have hn, then we are having output as yn equals to xn convolution of hn. Okay, then similarly we can convert it into the frequency domain, and then we can get the output y of omega, and then we can perform inverse Fourier transform in order to get to the time domain signal. Now the problem I have already told you that in discrete time Fourier transform, what we are having? We were having that the inverse discrete time Fourier transform, it was implementing integration, which is a continuous function. Now due to this reason, the transform could not be implemented in the digital systems. Now due to that reason, this discrete Fourier transform, it was then developed. Okay. So what does that mean? What does that mean? If we go back to the previous equation, x of omega, it would be discrete in nature, but x of n, it would be a continuous time signal. Okay, but the problem is that we are not able to implement these transforms in the digital systems. So we need a transform where, or the values where which would be discrete, and those discrete values would be handled by the digital systems. Okay, so that means we have to convert this continuous time domain into the discrete time domain, and this is what this discrete Fourier transform is. This is a very good chart. Okay, this is a very good chart. It explains what is happening in discrete Fourier transform. So we have a signal in the time domain. Okay, we have this signal. So its corresponding, if you perform the Fourier transform, its corresponding frequency domain component, it is given over here. Okay. So what we are doing, discrete time Fourier transform. Initially we are having discrete time signal. So this continuous time signal has to be converted into a discrete time signal by the process of sampling. So this is the impulse train. Okay, so this is the impulse train. So when you multiply these two, we convert this continuous time signal to a discrete time signal. And if you look into the frequency domain, we have the frequency component of the signal. The Fourier transform of an impulse train is also an impulse train. It would be something like this. Okay, so if you see, we are giving multiplication over here. So if you see, now as soon as we get this discrete time transform, and if we perform the Fourier transform over here, what we get? We are getting frequency components which is repeating itself. the original frequency component, it is repeating itself. Why? Because in the time domain we have multiplied, however in the frequency domain it gets convoluted. Okay. For calculating the output of the LTI system, we saw what we saw. Convolution was in the time domain and multiplication was in the frequency domain. So the vice versa also happens. If we perform convolution in the frequency domain, you get multiplication in the time domain. So here in the time domain we have done the multiplication, and due to the convolution factor, what is happening, this frequency component, it is repeating itself after every 2 pi. Okay. Now since it is repeating itself, what we have to do, we have to take the continuous time signal which is band limited. Okay, which is band limited. Why? Because if you do not limit the band frequency component, say for example, say 0 hertz to say 100 hertz, if you do not do it, then what will happen? When it is repeating itself, then there would be overlapping. So say 0 to 100 would be there, and again some components which are repeating itself, they would overlap with the system. Okay, so when we are doing the sampling, we have to band limit the signal before going for the this uh, before going for the sampling. Okay, now why it is done? This is because of a criteria which is regarded as Nyquist criteria, which says that the sampling frequency should be greater than equal to 2 of maximum frequency. And as I told you, any continuous time signal, it is having infinite number of sinusoidal signals. So frequency components above this FM would also be present. So to make our system capable of handling whatever the signal component you are trying to analyze, we have to band limit the signal such that this Nyquist criteria, it is being followed. Okay, the Nyquist criteria, it is being followed. Okay, so you have to choose the characteristics of the impulse train which is related to the Fs, because that this impulse train, how much will be this delta t, it would govern what is your sampling frequency. 1 by delta t, small 1 by delta t, it is your sampling frequency basically, right? So to get this sampling frequency, at what sampling frequency you will be sampling the signal, you need to know the FM. But for a continuous time signal, we have the FM equals to infinity, which we cannot handle with our digital systems. So because of this reason, we have to band limit the signal, so that in the frequency domain, when the frequencies are repeating itself, they do not get overlapped. Okay. Okay, this is done. Now what? Now we know that the signal what we have got is this one. Now herein, if you see the frequency component, it is continuous in time. Okay, so it has to be sampled. Okay, it has to be sampled. Now since it has to be sampled, so in the previous case, if you see, When we are sampling in the time domain, we went for the band limiting. Similarly, when we would be sampling in the frequency domain, we have to time limit the signal. Okay, we have to time limit the signal. So we will be using a filter window, which is basically a window, to get a section of the signal. To get a section of the signal, and once we get that, we got this time limited signal. Its Fourier transform is like this itself. See, it was quite smooth over here. After time limiting, it has got somewhat wonky. Okay. Now, once we have time limited, we can go for the sampling in the frequency domain. Now, once we have sampled in the frequency domain, see the time signal, it is repeating itself. Okay. So, band limiting and time limiting are of utmost importance when we discuss about this discrete Fourier transform. Okay. Now, in this case, if you see, both the time domain signal and the frequency domain signal, they have been discretized, and since they have been discretized, we can uh, go for the this we can use both the signals in the digital system, both the forward transform and the inverse transform, and we can implement that in any of the digital systems. Okay. So if you look into this these equations, DFT and IDFT, so if you see both of them, they are now discretized. Okay. So herein, if you see, there is one equation, one component W K N N, and it is regarded as Twiddle factor, and this Twiddle factor, it is given by this Wn equals to e to the power minus j 2 pi divided by n, and if you talk about the Kn, so it becomes this one multiplied by k. Okay, it goes in the numerator. Okay, so using this factor, we can go for the calculation of the DFT and IDFT. Now, if you see these two factors, in DFT it is normal Twiddle factor, in IDFT it is the conjugate of the Twiddle factor because of this minus sign. Okay. And if you see, there is another minus sign over here. Now, how to calculate the Twiddle factor for any given Twiddle factor? So what you have n k, so you have 0 1 2 3 so on, then you have 0 1 2 3 and so on, say n, say here also you have n. Okay, so Wn, what would be nk? 0 0. Similarly here 0 0, at this location 1, at this location 1 multiplied by 2, at this location say 2 multiplied by 1 2, at this location 2 multiplied by 2 4. Okay, so this would be your, in the matrix form, this would be your calculation for the DFT, and this would be for your IDFT. Now herein in the IDFT, if you see, 1 by capital N component is there. So capital N is the signal length.